Howdy, everybody. Hope you're having a wonderful time whenever you are. Um, we are on day 21. It's been a great year so far, and I realize, at least for some people, the holidays are probably coming up. Might be harder to finish these. We'll see how well I do as well. Um, Especially on the 25th, I'm super busy, so I may try and do it the night before and just finish it up. We'll see, just depending on how much time I have. So, but today was a really fun day. It was a day that helped remind me how much dynamic programming and memoization can take a nearly impossible problem and make it extremely easy. And we've seen that a couple times before. I think the big things that stuck up got in my way were the AI, first of all, having the AI help me, Chat GPT or whatever, finish my lines in my code and stuff. So we'll talk about that. And also just understanding what was being asked. So with that, let's dive into it. And so it's called Keypad Conundrum. And the idea is you're trying to get into a locked room, and you actually know the code of the locked room. The problem is, so here's what the keypad looks like. That in front of the locked room, the problem is you just can't go there because something is wrong, and there's different reasons. You'll see in a second why different rooms are wrong. The reason why they're wrong is really just part of the story and not part of the actual problem. But the idea is you have this keypad, and you're going to tell a robot how to enter the keys. And the robot is going to start here at the A. So he's going to have a finger. It's going to start here at the A. And if you tell him to hit 2, you need to, instead of just saying, hey, hit the 2, you need to say, hey, move left and then move up. Or move up and then left. And then you'd say, now press the button, right? So if you think about the series of steps you tell it to do, is you'd say move up, move left, push the button, and then that would push the 2. So if you got a whole sequence that was like 029A, what you would want to tell the robot is you'd say, okay, move to the 0, press it down, move to the 2, press it down, move up, that puts it over the 2, press it down, and then move up, right, press it down, and then down, 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 press it down, right? Basically you're giving the robot very specific instructions what to do. And so that's not hard. Apparently time's an issue though, and so they want you to find the shortest path to do that though, right? And you have to stay on the keypad. So there's no going off the keypad or going over here. If you want to go from A to 7, you now need to, what is the shortest path to go from A to 7, right? And it's here, 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 here. But also here, here, and all the way up, and then over here is the shortest path. Here and all the way up and over here is the shortest path. And then you can do all kinds of variations on that, right? There's actually quite a few ways to go from A to 7. But your goal is to find one of the shortest paths. Now, here's where the complexity comes in. They say the keypad that you use to control the robot looks like this, but you also can't touch that keyboard or that keypad because something's in the way, or there's some problem in that room as well. So you have to go to another room with a keypad that you actually can't get in as well. There's a robot in that one. But you do have access to the keypad of that robot. So this had me confused for a little bit, but hopefully, I presume once you read it is, you are right here and you have a little keypad with your arrows, right? And it looks like this. And then you're going to talk to robot 1 and he has the same keypad. And he's going to talk to they're going to talk to robot 2, and they have the same keypad. And then they're going to talk to robot 3, who has the number pad, right? I didn't do that very well, but you get the idea, right? Is like, so you're going to push a button and it's going to cause this robot to move. And eventually you'll tell it, hey, you'll say hit A, and that will tell them to push a button. And then all of their moves are going to translate into moves down here and down here. And your goal is to, like, so if you want this robot to tap 029A, this robot's going to have to do, you know, a bunch of these moves that look like this. Right? This is not the actual thing. So in order to get to 029A, you have to have this robot type in a bunch of key things on their keypad. And in order to do this, you have to get this robot to type in a bunch of stuff on their keypad, and it's much longer. And in order to do this, in order for you to talk to this, to tell this robot what to do this, yours is like substantially longer, right? So you think about the order of that growing substantially. And the key to all of this is when you're reading through it, is they're saying, we want you to find the shortest path, right? So for the first one, if you're trying to hit 029A, the first robot can use these three things, right? These three sections or these three movements to hit 0, 2, 9, and then A, right? So you tell it to move to the right and then hit the 0 by pressing the A button. And then you tell it to go up and A to move to hit the 2. And then you go right, up, A to hit the 9. And then down, 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 A to hit the last A. So that's the gist of it. And you just to be clear, what it's asking is, what is the shortest path, or what is the shortest number of sequences? And this caught me off guard for a minute, because I was kind of just thinking, oh, well, if I know, if I do like a pre-lookup, some kind of pre-compiling of figuring out what moves I need to go from any position to the other, right? Like, say I'm on the keypad, I can show you again, and I'm at a 7, I just compute one of the shortest paths to get to an A, and then that path is, I can just use that path anytime someone says I need to go from 7 to A. And then in this keypad, you actually have two keypads that you're doing this now, right? If I ever need to go from the left button to the A, I compute one of the shortest paths and then just use that everywhere. That actually doesn't work though, right? And here's the problem is, in order to hit 029A, these are the three sequences that would do that for the first robot. But these sequences have to be entered by another robot, and then you have to enter sequences to trigger that other robot, right? Remember, there's this like depth of them. And so you actually don't know. So let's say like over here, in order to hit 029A, there are three sequences that can be used to enter that. But and so these three are the shortest, right? These are the shortest for here. But we actually don't know which of them up here are the shortest, right? This robot is going to have to enter a bunch of key sequences to get this short sequence. And so, like, let's say each of these take 5, right? But then up here, this robot may have to enter, there may be like 3 ways to do this one. So I'm not doing this very well, but let's say there's 4 ways to do this one, and one takes 7, 6, and 9. And then there's 2 ways to do this one, and it takes 8 and 5. And then there's 3 ways to do this one, and it's like 15, 4, and 12, right? You would have to try all of these until you found this 4th one that says, oh, this is the shortest sequence over here, so I actually want to use this one right here in this case. But that still may not be the answer. And why is that not the answer? This one may take 6 to get to this one right here, which is bigger than this one. But if you go up to your key input sequences, you're going to have a bunch of them, right? You're now going to have, 50, 60, 30, 24, 18, right? And these all correspond to different things. And it may be like the smallest one is actually this one right here, if that makes sense. So even though this one was slightly bigger than this one, and you would have normally picked this one at this level, this one actually becomes the shortest overall, because in total you only have to hit 18 keys to get this guy to do 6, to get this guy to do 5, to get this guy to enter 029A. So it becomes a huge expanding problem. I don't think I ever actually printed them out, but so we can print them out and look at it, and maybe I can kind of show you. Let's see. 4 KVN. Yeah, maybe I just do this really simply for the numeric paths, and then I do this. I believe the arrow indicator works, right? Okay, so if we look at the entries, you can see, like, for some of these going from A to 7, there's a whole bunch of ways to go from A to 7, right? Look, there's a whole bunch of them. And then for each, imagine your next thing is to go from 7 to A, which is probably is down here somewhere, I'm sure. It's another large set, right? And so you have to try all of the combinations of that one, and all the combinations of the other one, and all the combinations of the other one, and suddenly you have to try a whole bunch of combinations, right? And I think you can actually do part 1 just by brute forcing it, because you only have like 2 depths you have to go. Like, if you think about like this is definitely growing exponentially, but it's only growing exponentially twice, right? Or 3 times, right? So if you say this is order n, and this is order n squared, and this is order n cubed, or whatever, and n to the 4th, this is not, even though n may be, and this is not, in fact, I'm going to erase it because this is not actually what it is. But like, say, you know, this one requires 20 steps. This one maybe requires, somewhere on the order of like 30 steps. This one will require, like 50 steps, and this one will require 80 steps, right, in total. But in order to like consult all the options, you have to like try all of them in all the places. And so like the actual total that you have to do, that you have to consult to get like the shortest here, is it will look more like, oh, you have to do 100 here, and then you have to do 1,000 here, and then you got to do 10,000 here, and then you have to do like 100,000 here, right? But it's actually, I think it turns out to be a lot larger. It's somewhere on this order. It's maybe like a million, maybe. So it looks more like this then. You have to try like what am I trying to say? You're gonna have to try like a million different permutations of all these options, and it just expands greatly, right? And initially I had done it this way because I was thinking, oh, maybe I can just find all the permutations. But it became so large, there were so many of them, that I'm like, oh, I can't do this efficiently, is the way to think about it. And so what happens when you say like, oh, I can't do something efficiently? What should be going through your mind is, okay, well, is there some sort of dynamic programming I can do? How do I break it down? How do I make it faster? Can I cache some results? Can I do some caching on some of those things? And that's actually what led me to the dynamic programming with caching, right? Is like, you're looking at this, you're trying to do all the permutations, and you're like, oh, it's just going to go on forever. And so there's not really a reason to like, well, you can expect that the complexity of the problem is likely going to get harder. And in this case, it does. Part 2 just says, oh, instead of there being 2 robots in the middle, so right now there's 2, now there's 25, right? So it's much larger, the robots in the middle. So now you go from like this number to, I don't even remember what the answer was for part 2. it's some huge number, right? So thousands, millions, billions, trillion, like so you're in like the um trillions to quadrillions range that you're gonna have to test all quadrillion options for each of these, right? And that just doesn't seem feasible at the time. So I want you to think, then spend a second, and even if if you want to pause the video for a second and just ask yourself, how might I solve this in a dynamic programming way? Like what how can I break this down? And okay, so if you've just think about it for a second, what is it that you're trying to do? Is you're trying to take the you're trying to go from this to this and hit the A button, right? You actually start at the A, so I should say really you're trying to go from here to here and hit the A button, and then from there to there and hit the A button, and then from there to there and hit the A button, and then from here to here and hit the A button one final time, right? So you're trying to do that, right? So the question I think you can ask yourself is, can I break this up into little chunks and do this dynamically, right? If I can just find the shortest path from here and then just add that to finding the shortest path from here, and add that to finding the shortest path from here, and then add that to finding the shortest path from here, now I can just add all those up, right? And we've done this before with dynamic programming. Really what you're saying is, for the series A029A, I can call it once and say, hey, can you just solve A0 for me? And then the rest is 29A, right? And then you can solve, and so once you've gotten this, you can say, okay, so now I have A0. Can you solve 02 for me? And the rest would be 9A, right? And now you can say, okay, well, I've solved A02. Can you solve 29 for me? And then the rest will be A, right? And then I add this result to over here. So now I know what A029 is. Can I solve 9 to A? And then the rest is the empty set. There's nothing left. And so once I've solved this, now I just add these two together, and I get A029A, right? I get the rest of the thing. These should probably be pluses, right? What is the results of doing these things? And eventually that leads you to A029A, right? So that's the dynamic programming approach. Instead of trying to add the complexity of like doing this in a for loop like this, you can say to yourself, oh, I can just do dynamic programming. So you could do it in a for loop, at least for part 1. I don't know how you do it in part 2, because again, part 2 is for 25 robots in the middle instead of 2. But for part 1, you could potentially do this in a for loop. But you can say to yourself, oh, if I solve it with dynamic programming, I don't need that for loop, that like nested for loops. I'm still going to have a for loop because I'm going to have to go through each of these pairs. But I can just ask myself, like, hey, can I just solve this part of the problem? So that will hopefully turn a complex problem into a simplified problem, but it doesn't actually solve the scope, the broad size of the problem, right? You're still trying to or you still need to solve for potentially millions of solutions down here. So how do you fix that in dynamic programming? Well, we've talked about it before. Like the easiest fix for that is memoization, right? This one is not a good example, but you'll actually see in the other examples as you're building out. In fact, maybe I should show you one. This keypad one doesn't really help much, but if you look at like what you end up having to enter and what the robot after you ends up entering and the robot after that ends up entering, it's a whole bunch of stuff, and you actually start to see patterns. So you can see A right, and you see A right here, and then you see A right A, and then A right A. You get a bunch of, here's some triple A's, so A to A, A to A, A to A. There's a lot of what I'm trying to show is there's a lot of duplication within here, right? And so even within the own line, as it gets large, there's a lot of duplication, right? So A to A is here, A to A is here, A to A is here, right? These are all A to A's, and then you got an A to right, A to right, A to right, right, A to right. There's a lot of those. So memoization could help you there, right? And this is the key to this is, oh, if I've already seen this before at this level, like if this robot's already done A right, I don't have to do it again. I can just return the results of that value, right? So if I go through I have to go through it once, but once I've seen A right, the rest of the time I don't have to go through it in. I can just consult my cache, my memoization, and do that. And those are the two things that when you put those together, takes a problem that's very complex and makes it very simple, right? And so I'll actually be interested to see how many people did it this way and how many people have very complex solutions for part one and maybe then simplify it in part two, because I don't think you can do part two with it. So just to be clear, what part two says is, maybe I should step back and say, like, eventually what you do is you find, okay, in order to hit 029A, you have to do like this sequence, and this is the actual shortest sequence. And then you basically do some math where you multiply 29 by the length of this and 980 by the length of this, the shortest length, and then you add all those values up, and that gets you the answer to part one, okay? And so that's with two robots, right? So in summary, there's two robots, and then there's a numeric pad with a robot in front of it. And what part two changes is it says, okay, now it's still you, but there's now 25 robots in the way in between you and the final robot with the keypad. And so that's clearly the part where you're like, okay, I can't just do this in a kind of brute force kind of way. I got to think about a faster way to do this, if that makes sense. So given all that and me talking about, again, we're doing dynamic programming with memoization, what does that code look like? And let's step into it and just do a code review of what happened here. So I, at first, actually created some kind of like lookup tables, I guess is the way to think about it. Like, what are all of the shortest paths? So if you're looking at the keypads, right here and right here, you can see like the number of like nodes in your graph is relatively small. And so it's pretty easy for you to just find all of the shortest distances from all of them. And I did that just so I didn't have to calculate it each time. So I did some pre-computing is the way to think about it. I did some pre-computing of, now I know every option from A to 7 and 7 to 5 and 5 to 6 and 6 to 5 back and forth, right? Same thing with this. There's even fewer. So it's really easy to say, hey, I just want to pre-compute the shortest paths to everything. And so that's what this first code does if you see it. I'm using oncelock here, which is now part of the standard library. This used to be lazy static. We've probably talked about this before. I guess I don't remember. But essentially what I can do is I can create a static variable of a hash map using this oncelock. And the first time it's accessed, if it hasn't been created, it gets created. So it's kind of like it does the setup for you and then creates it and then returns it. So how do I do that? I just hard coded all the values, all the neighbors. There might be a way for you to do this without it, but it was really easy for me to just say, oh, from 7 to 4 you go down, from 7 to 8 you go right, from 8 to 5 you go down, from 8 to 9 you go right, from 8 to 7 you go left, right? So I just create all of the neighbors and then I create the values. And the reason I do that is because then I can it's really easy for me to just join up the strings, and I'll show you what that looks like in a second. But this is one of the parts where AI was not my friend here. Just to be sure, I do spend a lot of time seeing if AI can finish my line, and I don't have a problem with it doing that. Sometimes it will try and finish a whole block, and so whenever that happens, I try and review it to kind of make sure it looks okay. but invariably I'll miss some things. And this was the case where the AI actually got me here, right? Is like there were some of these where like this A was not down but up. And so I was not getting the shortest paths from the test input, right? They tell you in the puzzle, oh, the shortest path for this one is 68 or whatever, and I was getting 72. It was just not the right answer. And I had to go around and I'm like, whoa, what is wrong? What am I missing? And I had to go look in here, and the AI had helped me fill in some of these values, and they were not the correct values. And so thanks for the bug, I mean, it helps me a lot, but those type of bugs can be really annoying, right? When the AI doesn't actually help you. But anyway, so here I kind of like, here's my list of like points and or list of buttons, and then the direction you take to get to the other buttons, right? So then I can just do like for each of the buttons, do a Cartesian product of the each of the buttons as well. So now I'm testing every button against every other button, and I just call this find shortest paths. And this is just the equivalent to a BFS, right? We're just going to do a breadth first search. We've talked about this before, where we say, hey, go, we're going to add our start to the queue or to our path, and we're basically just going to go through all of the nodes, and but start from the start. And for each of those nodes, we're going to say like, okay, if I've reached the end, then the path that I've been collecting, I'm going to consult it and see is it part of the lowest set, my lowest path, and if it is, I'm going to add it to my paths list. Otherwise, I'm gonna bail out, right? Because it's not part of my lowest. That is to say, like the way to think about this first part is, let's say I'm trying to find the shortest path from 7 to 5, and obviously I get 7, 8, 5, and 7, 4, 5, but I might also get 7, 4, 1, 2, 5, because I'm literally doing a full breadth first search. I didn't try and optimize this at all because it was so small, and so I could get 7, 4, 1, 2, 5. I wouldn't want to store that because that's not actually part of my shortest, right? So that's basically what this is checking here. If I get the 745 or the 785, that would be in my lowest set, so I'm going to add that to the list. Otherwise, I'm going to break out of it. Then I just consult my visited. I don't want to like revisit a node. That doesn't help you find the shortest path. But otherwise, I'm just going to say, okay, what are all my neighbors? And then for each of my neighbors, make a clone of the path and push my new direction, right? So that's this right here, this part right here. What is my new direction? And then I just add that of my list of work to do. And notice I'm using a VecDeck here because we want to consult. I mean, because I'm doing a full one, DFS and BFS probably doesn't matter. But I was thinking BFS at the time, and so I wanted to use a VecDeck to get that done. Okay. So again, just really high level, all of this code so far, so like the first, 110 lines, is just pre-computation. What comes out of this is a numerics path and a directions path that has this stuff in here, like what I was talking about. So you can actually just consult it and say, hey, what are all the shortest paths from 1 to 9? And then it gives you all the shortest paths right here, okay? And it does that. So this is from keypad to movement pad, or number pad to movement pad, or direction pad, I think is what I called it. But there's also, I create a similar one. So there's this one, and then I create a similar one for this one, right? So I say, oh, if I want to go up, the way I get to A is I go right. Or if I'm at up, the way I get to A is to go right. And the way I get to down is to go down, right? Here's where you really have to think these through. I don't know if this was the best way to do it, again, because of the AI. But if you have some other way that you did that, I'd like to see it. It's potential that you could... you just have it in a grid, and you can say like, oh, what are my neighbors? And if I'm going 0 plus 1, it's this way. If I'm going 0 minus or minus 1, it's this way, right? Whatever. I guess I probably didn't say that right, but you might be able to figure out based on the delta of the 2 points which of these you should be using. Okay, but that's all I've done so far. Is I now have these 2 functions that will return static hash maps that just say, if I'm ever looking for A to 9, the shortest path is this, and there is no other shortest path in that case. Notice I also have the 2 to 2s, right? So like if there's ever like things where you're just like hit the same button multiple times, you'll be interested in that one as well, right? And so those contain the empty paths. The other way you could do this is not include those and then just do an option style thing where you say, like, if it's there, then use these. Otherwise, if it's not, I presume I don't do anything. I just hit the A button. This turned out to be easier because, as you'll see later, you actually have to like include pressing the A button in all the paths. You want to add that to all of them. I think, like I had mentioned that a little bit earlier, is like you're gonna move and then hit an A, then move, then hit an A. So those A's you need to like kind of add to your thing, if that makes sense. Okay. So there's all the setup. So now what is the actual work that we do right here? And so for both part one and part two, nothing is really different. I literally just call this function called find shortest sequence, and I give it the line, right? So I'm going to give it 029A, and then I just tell it like how deep I need to go. Is it 2 or 25? So 2 for part 1 and 25 for part 2. And that depth is important because each robot will do different things based on how far they need to move, to get the other robot to do their movements. And so you kind of need to track where you are, which robot you are, when you're saying find the shortest sequence. But I'll show you that in a second, like what it looks like anyway. And then otherwise, I'm just doing the math that the problem gives you, and then I sum that up, right? So that's all the main program really does, is just go through all the lines, call this find shortest sequence. With the result of that, do the math and sum those up, and that will give you the answer to part 1 if you use 2 here, and part 2 for 25, okay? So how does this find shortest sequence work? This time, instead of using my own memo, I tried to use the cached function. I think I've tried to do that before, and sometimes it works. I've had problems with it before, and the issue is like you really want these values to be like, I think the issue I was running into is they aren't sendable, or they aren't easily clonable, I think is what it was. And so you couldn't use like references, right? And so that's why up here I use these once locks to get me like a static hash map of these two things, because then I can just use these static hash maps here in the thing without having them as part of the parameters. So my only parameters to find shortest sequence are give me the sequence, the depth, and the numeric, whether I'm using a numeric or a directional keypad. And then I will tell you the shortest sequence, okay? And so what is the first step? Well, I just need to figure out what keypad I'm using. So I get the paths based on, if I'm numeric, I use the numeric paths. Otherwise, I use the direction paths. And so my first call, this will be true, because again, I'm going to work my way up. I don't know if I mentioned that. It's much easier, at least for me, I don't know how you do it the other way, but you reason about it by going up, right? So you know you have to go from A to 0, and then you just ask this robot right here, well, how do I do all those movements to get from A to 0? And then you ask this robot up here, how do I do all those movements to get these movements to cause it to go from A to 0, right? It's easier to work your way up, right? So you start with the numpad, and then you move over to the direction pad is the way to think about it. And then all I have to do is I append an A to the beginning of it, because you have to start with an A, right? Or the robot is at the A. And I call this tuple windows. And what this has the effect of doing is breaking up, doing the breakup part, which is like splitting them up into tuples, this part right here. So A029A, you end up getting the tuples A0, 0, 2, 2, 9, and 9A. And these are exactly the tuples you want, right? Because as we'd mentioned here, the dynamic programming approach is just to try each of these in succession and figure out their answer, and then the total answer is the sum of those things, right? So I break them up into those windows, and then for each of those windows, I go consult my path, and I say, oh, what are the shortest paths? So maybe I should rename this shortest paths. What are the shortest paths from those 2 points, right? Now, if I've reached the end, there was a reason I had to do this, and I think it had to do with it's because I don't have to call shortest sequence again. I could add a little check here and say, in fact, maybe should we try it right now? I had done this two ways because if the when it like the idea is if the depth ever goes like to -1. Oh, that was it. I can't set the depth to -1 by using a U size, and so I never get down here, and I do like a -1, and it would like fail, if that makes it would I'd get like a stack trace or whatever, right, by trying to subtract by one a U size by 1 or whatever. You might still be able to do this, right? I just did it in two ways. I said, oh, if my depth is 0, it's literally just the shortest of these paths, right? I don't have to check anymore. Again, there might be some way to add a sentinel up here that says, oh, if my sequence is an empty string, I just return the minimum of the paths. Or I just return 0, right? I return 0 if it's that thing. But for me, it was easier just to say, oh, here's the shortest path right here, and then that's my value at the end, right? The way to think about it, if it's just not making sense, if I'm up here at the very top, and I don't need to make another call, right? I don't need to do this again. I can simply just, here's my list of shortest paths. And I just get the one that's the smallest, right? Or here, I just get one of them that's the smallest, right? So I say, hey, get me the length plus 1 and return the shortest. And do you even need to do that? Now that I think about it, you don't need to do this. I think it came because I copied from here to here. Like, you might still get the same answer by just going like this. Oh, I don't want to print out the entries again. That does not give you the right answer. Yeah. Okay. So why doesn't that give you the right answer? Sorry. These paths can be of different. We want to get all of the paths because we might consult. How do I say this? You can see this one may not be a good one. I may not be able to find one. Some of these may only take 3 steps, but then others will take 4. Oh, here's a good one. Oh no, that's also not a good one. The gist is like there could be cases where some of them, all of the paths don't line up. Yeah, why isn't? Oh, did I do it? I may have done this wrong. I didn't add the +1, huh? Because they should all be the same, right? Yeah, there you go. Okay, yeah, so that's a simplification. Now that I'm reviewing the code for the second time, if we reach the end, we just pick, we just use the shortest path length. And why the +1? Because we gotta hit the A2, right? We gotta do the A1 or whatever, right? So it's this shortest path length +1 for that final thing. Otherwise, we need to find the smallest path among all the paths. And this is the part where we go into the expansion, right? Is we now say, for all of the shortest paths, try and find their shortest sequence, but now we're going at depth -1. So we do need to push the A onto the path at the end, right? This was a bug I ran into before. I was not getting the right answer on the test examples, and that was because you had to push the A button afterwards, right? So you can see here, I add that to push the A button. So this is the case where you're like, okay, I'm somewhere in the middle. I'm in the middle of these robots, and I'm going to start doing some of their sequencing I want to find the shortest one from this robot, and then you're gonna have to work your way up and find them all. But each time you go up, each of them are gonna have to hit the A button to cause the other robot to push their button down, whatever button they're on, right? So you add the A to the end, and you say, okay, can you find the shortest sequence for that part of the path with a depth -1? And now we're always going to be false from now on because we're going to be using the direction pads. Only the first time do we use the number pad. Okay. I actually think we can still tighten this up even more and do it shorter. But anyway, we just do that over all of them, and then we sum up the total of those the total of those values, right? So why is it the total, you might ask? Well, if you remember, what we've done is we've essentially said, like, what is the minimum distance from 0 to A? And let's see, that comes 5, and 7, 12, and 4. So we want to sum up all these values, and that is the shortest path that is this shortest path right here, right? 1928. Is that what it is? Like, that's what you're trying to do, right? Is figure out the shortest path. So again, we just iterate through each of those pairs, those tuples, and we say, hey, what are the shortest paths between those tuples? If it's 0, we just, obviously the first one is the shortest because they're all the shortest paths, and so we do that plus 1. Otherwise, we have to go deeper, right? We're going to go deeper up the stack and say, what is the shortest way for all of those? And you'll dig your way through and find all the shortest paths, and eventually you find all those together and you sum them up. The cached here matters, right? Like I said, you're going to be reusing things and seeing them again. And even for part 2, you will notice part 2 finishes faster than part 1. And why is that? Because you've already pre-computed, you've already cached a depth of 2, and so you never have to reuse any of the depths of 2 again, right? All of those are like pre-solved for you, and so you get those ones back immediately, and so now you just have to resolve for the higher numbers, and those are bigger for part 2. They're way bigger, right? I don't know if they actually show you the values in part 2. Yeah, they don't, because there's just so many. But the idea is, you can see how big the number is. It's in like the quadrillions. Imagine like if this is 2 levels up and it's just how do I show this? Oh, here, right here. So this is the 1 robot, the 2nd robot, and the 3rd. Imagine like the 4th one is expanding even more, and up to 25. It's just getting absolutely enormous. But there's a lot of duplication, right? There's this over A, or A right, 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 A right. It's all over the place. There's no reason to consult it again, to do it over and over again, right? And that's where caching helps you out here, right? I can try it without the cached, and it will just never finish. I promise it won't. At least I doubt it will. You can see it's already taking a while. We'll let it run. But again, hopefully this day is another example of, wow, dynamic programming and memoization can break down this problem. And I have to apologize if I did not explain this very well. First of all, it's because I'm tired. But don't take that as a dig against dynamic programming and memoization, because what it can do is amazing, right? To think about, like, here's how simple this problem is you just kind of recursively call this find shortest sequence on each of like the pairs of items, the windows of the items in the list, and then just recursively say, okay, find that shortest a little bit deeper, and then that magically solves it for the general case. But then you add caching. This is still not finishing. You add caching to it, and now it solves the whole problem in like microseconds, right? You get to this ginormous answer that, again, is in the trillions, where you would have had to consult like quadrillions of different things, and it would have just never finished, right? And now you finished it immediately. So hopefully that gets you there. Now, having said that, I do want to spend some time thinking about how I can optimize this even further. I did do some iterations. Originally, this was just in a for loop. And then I turned it into being more functional styled and mapping and summing. Part of me wonders if it would be more readable if I did have this sentinel. Like, the problem is you still have to consult the shortest paths. So if you imagine the case where the sequence is empty, map min. I'm struggling to see how you could change this, because you might actually not be able to. And the reason is like, this shortest path comes from the difference in these two, right? And so you say, like, what would the sentinel case like be up here? Is you'd say like, oh, if the sequence is empty, oh no, you'd say if the depth is 0, you still have to consult all of the sequences to figure out what their shortest paths are and add them up, right? So I don't know that you can actually change this part. Like, I'm trying to think how you would make this call up here, and the idea is the path, this depth would end up being 0. You'd still you still basically have to do this and still call shortest paths, and but you just say, oh, it's just a sum of their length plus 1. Anyway, okay, so maybe you can't optimize this or make it more readable even further. I don't know. Sometimes the functional does make it harder to read for me. Yeah, like the cases here are, oh, I just need the shortest path, or I need to go further until I get to the shortest path. I need to go further to see which of the shortest paths are best based on deeper down, right? That's the intuition about what this one's doing. Is it saying, I have multiple shortest paths. For each of those, I need to find out which one of those paths are the shortest if I go deeper in down the tree of robots, right? Each robot is going to expand the like list of things it needs to do based on what it got before. And so you need to go all the way up all the way through the robots to find out which one is the shortest. And then bring all those together by doing, and I bring those all together by doing a min. Yeah. So I do think you have to leave this here. If you can think of another way that would do this that would make it more readable, though, I would love to see that. Anything else? Yeah, I felt pretty good about the rest of this. I did review some of this stuff a little bit and add some comments and stuff. This again felt really weird. It would be nice to have the AI not mess up and cause some bugs in my code. But overall, this was really easy. And I largely just stole this from, if you go look at Lazy Static, the Lazy Static GitHub repo, it says, oh, the new equivalent of Lazy Static is just to use this once lock. And, excuse me, I basically just copy and pasted from that. So, and again, this is just to do pre-computing. So overall, how was the day? I thought it was pretty good. Some of my initial struggles were misunderstanding what the problem was asking. Like, I think my assumption was that got me failure is like, at any level of the robot, the shortest sequence chain does not affect the robot above it or the robot after it, right? But that's not actually the case. Is like, if you think about it, some of them are going to have to move in order to get from one point to another. you may have to move more spaces than if you'd found a shorter path. So you're actually like, the idea is you're trying to find the shortest path of the shortest path of the shortest path, right? Is like, of these three, which one causes the robot above it to have to press the least buttons to produce these? And numbers are those numbers are different than what these values are, because these are all the same length, right? So you kind of have to keep going down, turtles all the way down until you find the thing, right? So there you go. Again, I had a lot of fun with today. It was kind of interesting, kind of difficult, but you get there. And hopefully y'all didn't have the same bugs as me. Maybe it wasn't as hard. Okay, so this person visualized the robots. Yikers. Yeah, this is going to take a lot of time, right? But you can see like how much is involved substantially over the things. Oh, they may have just shown this on the test case, right? Like, part of me, when I was originally doing it, I thought, oh, they might have like, say like, oh, now there's 100 robots in the middle, or 25. And when I thought it was just a shortest path thing and not like a recursively finding the shortest path to get to the shortest path of in total, I thought, oh, can I use something like Tokyo to like have all the robots, and then each of them are sending inputs to the other robots, so I can kind of do the work in parallel and I don't have to do it like a bunch of times. But that ended up not being needed, because it turned out the real complexity of the problem is, first of all, can you figure out, the shortest paths? That's part of it. But the real meat of it is, how can you efficiently find a shortest path, where in order to find that shortest path, you have to like consult the next robot and say, which of these are the shortest path? And then that robot has to ask the robot above it, which of these would cause you to press the least keys, is the way to think about it, right? So anyway, something to think about. Well, that was fun. Yeah, now imagine this times 25, right? I don't, what's this even from? I'm sure it's from something super popular that I haven't seen, and people will laugh at me. Yeah, sometimes this happens. The input was really small, right? And it can be deceiving, because they're like, hey, here's the test example, and then here's the real input. You could probably get I wonder, like, these solutions probably are relatively fast compared to these ones. And like, why do I say that? If you notice, like 789A, it's very easy to do, right? You're just like, oh, go right, push a button, go right, push a button, go right, push a button, go down, 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 push a button, right? So that turns out to be really small, right? Some of these are relatively small, but some of these are like huge ones, right? Like, how do you go from 1 to 7 or whatever? And so I think when I was initially doing my testing, like some of these cases, or sorry, I was looking at it the wrong way. What were some of the cases? 4 to 0, 4 to 0, 2 to 8, those things. I can't remember what it was. It felt like when I was trying to see like, can I just brute force it? The test problems were coming back within milliseconds, but the input problems were taking a few seconds. And that's when I realized, oh, this is just not going to work to like kind of brute force it. And that's where I was like, oh, it's because of the exponential growth. And so that did cause a problem. But it can be a little, sometimes your input is like a single number and you're all like, okay, now I know bad stuff is going to happen. Taking a break at a party to check AOC. I do that sometimes. Like, I'm like, ooh, can I read what the problem is before I actually get to my computer? These are all the problems that they were talking about in the thing. They like high radiation, depressurized. It's very cold, so we need a bunch of robots to do it. Yeah, there you go. Very good. Having a robot enter a code, the robot is controlled by a robot. The robot controlling robot is controlled by a robot. The robot controlling robot. Yeah. I actually, the first time when I was trying to figure this out, recursion is really cool for this, so I totally agree. I I think I misunderstood the problem a little bit, and I thought the initial depth was 3 for part 1, and so I was like, "Oh, okay, the initial depth is part 3." And so that sent me for a loop too, and I wasn't getting the right answers for the test input. So that's a weekend puzzle. Uh-huh. Yeah, that is. I wonder if it's planned that way because there are definitely days where it feels like the weekend ones are particularly harder. I think though, I mean, I don't know what the average code length of lines are, right? We only get to like 200, and that includes a bunch of comments, and I did a bunch of pre-computing. Um, you probably figure this out on your own, but I actually don't think in this problem is the one of the hardest ones we've seen this year. But I guess I can't speak to weekend versus non-weekend. I do think they're. I kind of agree with this sentiment, so it may be right. At least it's not. Oh, it is. Well, that just sounds like 2D grid with extra stuff. It is a 2D grid. You do have to find the shortest paths. And again, because it's so small, you can kind of just do a breadth first search and efficiently do it. Obviously, you can still use, whatever Dijkstra's. I don't know that they help you, but you actually had two 2D grids in this puzzle. You had to, and at least for me, I was like, oh, I can just pre-compute the shortest paths on all of the 2D grids. It'd be interested to see which of them were used. Like, was it worth it to pre-compute? I don't know the answer to that. Billions. It's not billions. I think it was trillions, right? At least mine was. Let me look at the number again. But it is a big number, right? One, two. So hundreds, thousands, millions, billions, trillions, 167 trillion. Yeah, that's a lot of robot. That's a lot. You have to enter 167 trillion uh, button presses. You have to do 167 trillion button presses to get all the robots to do it. So good luck. What? Are they the same picture? I mean, they're in reverse. How does the A and O and A being down here? Reading is one. Oh, they did it the wrong way. Okay. But the meme doesn't make sense because they actually aren't the same, right? You get into trouble if you do it this way. You're gonna find different paths. That's a bummer. Yeah, I did not. I didn't read this part wrong. But again, the AI, man, it got me on that one. I was annoyed. I spent a while like, what am I doing wrong? Am I off? Am I doing like an off by one? And so I was adding one's places, removing one's places. No. Oh, day 17. Let's see. Day 21, terminal visualization. Oh, that's cool. So you push the keys and then it tells you how to do those things and it kind of goes through. Help you like visualize it. That was interesting. I'm trying to think of like did I use any visualizations in my mind? And I really just like the hardest part was when I was doing trying to create all the entries for here is I kind of just consulted this. I'm like, okay, I'm going to start at the 7 and that can go to 4 and 8. Then I'm going to start at the 8 and that can go to 7, 5 and 9, right? So that I didn't really have to draw anything out. There's days where you do have to. I didn't feel like I needed to this time. Maybe you did though, and that's fine to help visualize yourself what's going on. I definitely did some debugging early on where when I wasn't getting the right answer is like, okay, well, what is the initial robot pushing? And then like what are the robots in the middle pushing? And then what am I pushing to kind of like see what's going on? So um what is my purpose to press the button? Oh, these are annoying. Holy cow. When it's not necessarily these ones, but like when it's asking you to enter your password on the thing and they don't have an option to like scan a QR code or whatever and log in from your phone. These are really annoying. Man, I hate those. But that's hilarious. It is kind of like this, right? That's I mean, maybe you get your ideas from anywhere. Just 250 trillion. Yeah, mine was 167, but there you go. Yeah, it is trillions, right? That's hilarious. We could have gotten Data to do it. Although he's one of the robots, but I guess he could help us. Oh, do they really meet at -40? I guess I haven't paid attention to that. That's cool. Okay, let's finish off by just looking at some of the solutions. Uh, uh, I pre-computed all the possible paths between every pair of keys on both keypads. Changing directions would be costly. Changing directions would be costly. Oh, that's an interesting idea. So they're doing the pre-compute here as well, but if you imagine like the shortest paths, do I still have those up? It's like this one is probably faster than this one because this one just entails the next person like getting to the down arrow and then just hitting this twice and then going to this one and hitting it. Whereas this one is get to this arrow and then go to this one and then go back. There's no like, oh, I can just hit the button twice. That is an interesting optimization. That's a cool idea. Like you can say like this one won't, or you can infer that like this one won't produce the shortest path because it has, the least number of like similar things, whereas these two might, just depending on where you currently are. Interesting. That's cool. Okay, I like that. Very fun. Should we look at how it's done? Here's the numpads. Creating all the paths. So it looks like it's this is good is determining on how good it is. I'm trying to grok with these. Oh, R and C are the positions, the rows and columns. Why does it make it bad if the row is 3 and the column is 0? Yeah, I'll have to think about that for a minute. Like, how do you figure out what makes it bad? And like and maybe I'm just not understanding what's happening here in the code. I'd have to read it maybe a little bit closer. But my inclination would be is like as you're building up the paths. So I could do this too here. Like as I'm adding these paths, I could do like a delta of the or I could keep track of also the previous direction and then just the number of times. And like if I get up here, I'd have some other value that was like the number of times that I turned, and I'd say like, oh, if the turns are greater than um, how would I do that? If the turns are greater than the number of turns in all my other paths, maybe I don't add them. Anyway, that's a cool idea. I like that. That's fun. Very, very. That's very mindful too. Is to say, oh, I can. Uh, like what was going through my mind is I just don't know which of these three are going to be the best because they change based on like what the robot above me is going to do, and then those change based on what the robot above, and so on and so forth, right? And so like my thinking was is I just don't know. But this is an interesting deduction, is that changing directions is going to cause the robot above you to do more work. And so the more you change directions, the worse you get. And so like of the three, oh, maybe that's what you do, is after you've collected all the paths, you determine how many times you change directions, and then you prefer to keep all the ones that are the smallest. That's how it would work. That's how you would do it. And maybe that's what they're doing here. I just have to read through their code and understand. But that's a cool idea. Today took a lot out of me. It was really hard to debug, and I kept running in. Yeah, I did. Today was one of my longer solve days. I actually started it last night, and then I was just like, oh, I have to go to bed to finish before I finish this. And most of my debugging woes were last night. So part of it was maybe that I was sleepy and just not paying attention. And so in total, it was probably one of my longer solves, just because I did have a lot of bugs from the AI and from myself, like missing the add the A type thing. That took a little bit out of me. Moving over the gap. Oh, like right here. Like from here to here, you might say, oh, I can move to here. But you actually can't do that right now. You get an empty string here. I see. It does tell you that somewhere, is like you can't move off the grid. Yeah. So that would be a bummer of a bug. Like, how did I? Well, I just pre-computed all the paths, right? And I pre-computed all the values, right? If you turn this into like a grid and this was a space, you'd probably have to do some checks and say like where it's not a space or whatever, or some other value. You put a dot in there and say where it's not a dot. Let's see, TypeScript. There are two key parts. For each move, I decide on the best control sequence. There is only one choice when the robot isn't moving in at least one of the axis of movement, or if an otherwise valid option would move over the gap. In all other cases, I take two options that maximize repeated pre-press. Maybe minimize. Oh, maximize repeated key presses. Yes. Yeah. So you say like, oh, this one because it's just like right. I'm just hitting A bunch of times. Okay, it looks like maybe it isn't solved recursively, so let's just go, or solved with memoization. I don't know how you would though, but let's see. Find nested path. Find min path. Yeah, so if you see them set up like this, you have to say to yourself, "Oh, from here, this is I can go up here, but I should not because it's this space, right?" Yeah, I'm not quite grokking the TypeScript here, but it feels like what they're saying here is you've got a bunch of ways that you want to go. So you like find where you go from start to end, and then you ignore all the ones that don't have like the lowest number of turns. Interessant. If that works, that's really interesting. This would be another one to try and solve this way, because like what it's suggesting is like you don't actually have to do dynamic programming. Well, you still probably do the dynamic programming part, you just don't memorize it. And what is the effect of this? Maybe the way to think about what's happening here is, for some of these I have to consult like 4, and then five or six of them, and so I have to test 4, then 5 or 6 and stuff like that. um but if you make the deduction that you want to take fewer turns, and so you only, like, let's say you only do this one and this one because the rest in the middle have a bunch of turns around them. Maybe you pick these two in the middle too because they also have fewer turns, but you ignore like these two. You've gone from now 6 choices to 4, and that compounds, right? Remember these numbers over here, they start growing. Well, now maybe you go from like 100 total to 30, and then this only goes up to like 400, and this goes up to like you know uh 1,000 or whatever, and then this one goes up to 10,000, right? So now you're only doing like 10,000 as opposed to a million, right? This should not be a check, it should be this, right? Like that's the idea, is because you're reducing the branching, you're reducing like the overall total number of like space, that the overall total space that you have to check, right? So that's cool. I would not have thought to solve it that way. But again, finding that deduction is pretty cool. Eric is the Advent of Code guy, has always said like he does. I think we've seen this before. Is he doesn't like to give out the quote unquote correct solution, because there is no correct solution. Like the question is like, could you solve it? And if you could, good job. And I agree with that sentiment. So, and this is what makes it cool, is to actually see different ways that people did it. I'm very familiar with, graphing algorithms, dynamic programming, those type of things, and some of the other more arcane things like shoelace and things like that, right? I keep saying shoelaces. That's what it's called. Shoelace formula. Shoelace algorithm. Okay. The ropey one. It's like the crossing is what's happening. Okay. So like those type of things I'm like kind of familiar with, I guess is what I'm saying. Um, but it's also important to be able to make these deductions, right? We've had days before where looking at the puzzle and looking at the input and like making deductions about it that distill it down into like a smaller problem are also important too, right? So finding these things, like I say, kudos to you for finding those type of things. That's really cool. I did not see that. Um, okay, so it sounds like this is the thing. Instead of just building strings, you count transitions, kind of along the same style. Okay, very cool. Yeah, that's crazy that that works. I approve. I think that's cool. It's a pretty basic DP problem, although a bit tricky to implement. I created 2 compile time evaluation functions, num, which computes the number pad lookup table, and pad n, which computes them. Okay, so using consts like this, and then you must just have like a what is the value here that uh oh, you already have the oh, you have each of the positions and then you calculate the distance of each of the positions. So it is like a pre-compute. These arrays are like really big. How do you determine when the array's done? Because not all of them are the same size, right? Oh, it defaults to 0. That's true. None of them would be 0. So you can just stop when you find one that's 0. Okay. Okay, very cool. Let's look at one more. Yikes, this first day I had to stop, sleep, and try again the following day. This was exactly me. Yeah. Depth first recursive algorithm using caching, where each layer deeper is one robot closer. I mean, this sounds similar to mine. Let's just go look and see. Okay, caching. I think pre-computing, I said caching, but I think pre-computing is actually a helpful one in here. Because it happens so fast, if you're just trying to like solve it as quickly as possible, you probably don't have to worry about pre-computing. If you just have some function that says like give me all the shortest paths and then you just reuse that function over again, I mean that probably works too. Okay, let's do one more and then we'll look and see how it does. Yep, chains of robots. Okay, so put into a coordinate system and then oh, this is like determining the sequences, like how do you get from one to the other? Yeah, caching to avoid sequences. So yeah. Okay, there. You have a map here that says like, "Oh, here's the shortest." Okay. Let's look at the actual code. People have these utils. I wonder if I should start doing something like that. I see that a lot. You do a lot of the same things and having like ready-made things like Dijkstra's, those type of things, like algorithms that are used a lot might help. Anyway. Okay, so there's his like different mappings, get sequence. For each line, split the line, get sequence starting at A. Yeah, okay. So you start at A and there's your rest, and then here's your num map. This is like how you go from one to the other. Count the sequences, add them all. What is this A to I, no error? Oh, do they just literally ignore the error? Okay. That's kind of a cool thing to do in Go. Normally you'd have to like get the value and replace it. And so maybe you add some wrappers around this. It's the equivalent of doing an unwrap in Rust, right? Okay. Very cool day. I had a lot of fun doing it. Again, it took a little bit out of me. And I had to do it over 2 days because I had to you really had to think about. That's the crazy thing about like recursive programming and dynamic programming is like, you're trying the brute force and it's just not working. And you have to stop and to yourself and say, hey, is there a better way to do this? Right. And then you ask yourself these questions like, how can I break it into pieces? Or, you know, what would a table look like if I was trying to solve chunks at a time to bring me up to the final place, right? So that's what makes these days fun and these puzzle solvings fun. As always, I love Advent of Code. Things are going. I'm really enjoying the days so far. Hopefully, you've been enjoying them too, and you've been enjoying me doing the solution reviews and stuff. If you have any thoughts or better ways to do it, I'd love to hear from you. Let me know. Otherwise, I guess we'll talk to you tomorrow. Bye.